Welcome back to Computer Science 3200. Today, we have our last lecture on reinforcement learning, where we'll be talking about temporal difference learning, and most notably the QLearning algorithm, which is one of the canonical reinforcement learning algorithms. Then after the lecture won't be too long, but we will be going over assignment 5 today. Let me just turn off my phone ringer real quick. There we go. And I'll be going over assignment 5, and assignment 5 won't be too difficult. A lot of assignment 5 is already done for you. You just have to fill in a couple of blanks with stuff from the lecture slides. So let's jump right into it, shall we? Oh. Here we go. So today we're going to talk about a little bit about on-policy versus off-policy learning. Then we'll talk about what temporal difference learning is. And then we'll talk about two of the most famous temporal difference learning algorithms. We'll talk about SARSA and QLearning. All right. And on-policy versus off-policy learning is chapters 5.4 to 5.6 in the textbook. So there's a little bit of reading to this. I recommend reading that before the exam, but we're just going to briefly go over what it means in the class today. So on-policy versus off-policy learning. What does that mean? So first, let us recall the Monte Carlo exploring starts algorithm that we showed before, right? So we have a Monte Carlo algorithm that's going to go through an episode before it updates returns. What we did with that is we used the current policy to update the values, and then we used those values to update the policy. Okay, so in that example that we showed last time, we are improving the same policy that is used to make the decisions or guide the learning. That's called on-policy learning. Okay, and off-policy learning, off-policy methods learn a different policy than the one that is being used to generate data. So for example, we could use human or random actions to learn a policy if we want. So just think of if we were playing blackjack, right? So last time we showed, okay, we're using some policy to guide our actions playing blackjack, and then we get values from that policy, and then we use those values to update the policy again. So the same policy is guiding our actions that is being actually updated when we do the update the policy step. However, for example, we could learn about blackjack by just doing random actions if we wanted to. So if we had just taken a bunch of random actions like hit here, stick there, we would still be learning about those values and we could still update a policy, but we were using a policy, random, which isn't the policy that we're learning in order to guide the actions. Okay. So similarly, we could do reinforcement learning by observing a human playing, right? So I could have in my blackjack user interface or whatever for my project, I could let the human play. And based on the rewards that the human got, I could then be forming my own values and my own policy based on those values. So if you're using a policy to generate actions for learning, such as human or random or whatever, and then you're updating a different policy, then that's off-policy learning. So this is Monte Carlo policy iteration. Remember, so we have some initial, we covered this last time. We have some initial value estimates and we have an initial probably random policy. And then while true, we generate an episode based on that policy. Okay, so that's this part up here. We generate an episode and we update the value estimates based on the episode returns. So based on whether or not I won or lost that hand of blackjack, I'm updating my values based on that. And then in the second step, I'm updating my policy to choose which actions gave me the maximum value estimates. All right. So in on-policy learning, we generate episodes based on the same policy that we update. All right. And in off-policy learning, this generation of the episode, when we generate that episode, we are using a different policy than this P here. Okay, so that's what off-policy is. Now, it doesn't have to be random actions, could be human actions, could be different, just something that's different than the policy that we're updating. That's called off-policy learning. So OnPolicy updates the same policy that it used to generate the actions, and OffPolicy updates a different policy than the one that was used to generate the actions. So OnPolicy Learning learns a policy that takes exploration into account. Okay, that's very important. OffPolicy Learning may not take your exploration into account. And so it could have poor online performance, but it may result in better performance after the learning. So we'll see what that means a bit in a second. So in OnPolicy, the policy is generally what we call soft, okay? So a soft policy is one in which you have a chance to select any action, okay? So there's never like a hard policy, which means you always take this action. So the chance to choose every action is always greater than 0. So that means that pi, so your policy pi, so within your policy pi, the probability of choosing an action A at state S is always greater than 0 for all S and all A. As it learns, the policy moves towards a deterministic optimal policy. So one example of OnPolicy methods is to use an epsilon greedy policy to select actions. So epsilon greedy is a soft policy because with epsilon greedy, there's always some non-zero chance that you're going to be selecting any action, right? Because you're going to select a random action sometimes, and that gives you a chance to select any action. So we would call this epsilon greedy OnPolicy control, right? So with probability epsilon, we choose a random action at any state. With probability 1 minus epsilon, we choose a greedy action at the state. So in an epsilon greedy policy, non-greedy actions have probability epsilon divided by the number of actions, and greedy actions have probability 1 minus epsilon plus the chance that they could be chosen randomly, right? So this is an example of an epsilon soft policy because it means that the probability of choosing any action at any state is always greater than 0. So it's greater than epsilon for some values, namely the greedy actions, and it's for some epsilon greater than 0, it has this probability of being chosen. And I'll show an example of this once we get into the algorithm to show you like that, yes, there is a non-zero probability of choosing any action. All right, so Monte Carlo generalized policy iteration, epsilon soft policy. So OnPolicy Monte Carlo is still generalized policy iteration. We still go through that circular process that we were talking about. We use first visit Monte Carlo to perform policy evaluation and estimate our current policy. Without exploring starts, if we simply make our policy greedy with respect to QSA, which is the action value estimates, we would never explore and many state action pairs go unvisited. So we talked about that last time, right? How we may need exploring starts. But for some environments like blackjack, because there's the dealing of the random dealing of the initial hand, it sort of has that exploring starts built in. So for blackjack, we wouldn't need to worry about this, but for some environments, we do need exploring starts. Epsilon soft OnPolicy methods ensure that exploration occurs and all state action pairs eventually get visited. So what that means is that because epsilon soft is randomly choosing some actions sometimes, if we are not always choosing the greedy action, and sometimes we're exploring randomly, then we have a chance to, at least a chance to visit all state action pairs in our environment. However, the policy we learn is now only optimal within all epsilon soft policies. But in practice, that's still quite good. So what this means is a little bit hard to wrap your head around, but I'll have an example later called the cliff example, which will show you what I mean by that sentence. So if you don't get that yet, okay, it's okay. We're going to give an example of that a bit later in the lecture. So OnPolicy methods update the policy with the randomness of epsilon greedy included. It means that if you're using epsilon greedy to generate your episodes, the policy then thinks, okay, well, the eventual policy I'm going to have takes in that randomness into account. So if the environment has like hazardous features with strong negative rewards, epsilon greedy is probably going to encounter them at some point, right? And this results in a policy that can be overly cautious and not necessarily globally optimal. And again, there'll be an example of that in a little bit after I show the algorithms. So here's the algorithm for OnPolicy first visit Monte Carlo with epsilon soft, okay? So initialization, we're going to have Q of SA is going to be some initial value for each state, and P of SA, that's our policy, so some initially equiprobable policy, okay? And this is essentially the same algorithm that we had before, except now, instead of just choosing the highest valued action, we're implementing epsilon greedy into this, okay? So we're going to generate an episode using the policy because we're doing OnPolicy learning. Then, for each tuple, meaning for each state action reward, remember our episode is state action reward, state action reward, state action reward. So for each tuple in the episode, since this is first visit MC, we're going to sum all the rewards following the first occurrence of this state action pair in the episode. We talked about that last time. Then we do our update function. So this is the any update rule, right? This could be the sample average, but here we've got the step size incremental update. So we take our previous estimate and we add to it the step size times the new return minus the previous value. Okay, so we talked about that before. Then we have to do the policy updates, right? So this is updating our values, and now we update our policy. So for each state in the episode, we're going to select the action that maximized our QSA. So we have QSA for each of our actions. Let's say we have like move up, down, left, and right. So we're going to look at the value of going up, the value of going down, left and right, and we're going to store which one of those actions gave us the maximum value. Let's say it was going up, right? So here, A star would be up. It's just saying choose the maximum A for QSA. Then for each action, and this is going to be our greedy action, right? Then for each action A in all the actions at state S, if A is the greedy action, right? If this is the maximum action, then our probability of choosing that action is going to be 1 minus epsilon plus epsilon divided by how big, or the number of actions. Otherwise, if it's not the greedy action, then we just have that epsilon random choice of doing it, so the probability of choosing it is epsilon divided by the number of actions. All right, now let's do an example with actual numbers so this makes a bit more sense. So here, for example, this is what's going to happen. We're going to be at a state XY, and we're going to have, let's say, 4 actions, right? So maybe up is action 0, down is action 1, left is action 2, right is action 3. So here's an example calculation. So we're going to have, this is what we did before. This is the code that updates our policy, right? So here's an example. Let's say we have epsilon equal to 0.1, and the number of actions is equal to 5. So these bars is the cardinality of the set, right? So the cardinality of the set is the size of the set, which is the number of actions. So epsilon equal to 0.1 means we're going to be taking a random action 10% of the time, right? So let's say that we have QSA values at a particular state equal to this. So action 0 has value 10, action 1 has value 20, 2 has 15, 3 has 5, and action 4 has value 10. Okay, so what we do is we say, let's calculate argmax A for QSA. Well, the action that gives us the maximum value is 1, right? Because this is, well, it's action 2, but it's index 1. So A star here, that just means the best action, the index of the best action is 1. All right. So when we go to update our probabilities for our policy, here's what we do. All of our, up here, it says if it's not the greedy action, so if it's not episode 1, okay, then it's going to be 0.1 divided by the number of possible actions. Let's think about it. If we have 5 possible actions and we have a 10% chance of choosing a random action, what is the chance that any given action will be chosen? Well, it's 10% divided by 5, right? Because we're choosing a random action 10% of the time, and then we have a 1 in 5 chance of choosing this thing as the random action. So choosing action 0 will have a 2% chance of being chosen, which is 10 divided by 5, right? Similarly, action 2, 3, and 4, they also have that probability of being chosen. However, because action 1 is the greedy action, well, epsilon is 0.1, so 1 minus 0.1, that's 90%. So 90% of the time, we're going to be choosing this action as the greedy action, but we also have that 2% chance to choose this action as the random action, okay? So what we end up with for our policy is 2% of the time choose action 0, 90 plus 2% of the time choose action 1, and then 2% of the time for the rest of them. Okay, so I hope that makes a little bit more sense, and now this calculation makes more sense. So in this example, remember that epsilon was 0.1, so the chance of choosing a non-greedy action was 0.1 divided by 5, which is the number of actions. And then for our greedy action, we had 1 minus epsilon. That's the 90% chance of choosing it as the greedy action. And then plus, we have that 2% chance of choosing it as the random action. Okay, so that's why these values are down here. And this is a perfectly reasonable question to ask you on an exam. Okay, so if I give you this, if I give you this, all right, then you should be able to do this. Okay? So if I give you those first 2 lines, you should be able to do that calculation for me on an exam. Wink, wink. Nudge, nudge. All right. Someone asked a question, does epsilon always have to be a static value, or do algorithms update its value during learning? That's a good question. So what some people do in some algorithms is a good strategy is to have a high exploration to start with, but then taper off the exploration as you learn more and more. And that's something we talked about. Well, UCB kind of does that for us, but we're not doing UCB right now. So some people in some algorithms do actually lower epsilon over time, but we're not talking about that right now. So yes, it's possible, but we will not be doing that for our assignment, okay? Now, OffPolicy methods. Let's talk about that. Excuse me, my nose is super itchy for some reason. Alrighty, so here's the learning control methods dilemma. We wish to learn action values based on what we currently believe to be the optimal behavior, but we need to behave non-optimally in order to explore the state and action space and to actually find the optimal behavior, right? So this is exploration versus exploitation, right? I want to behave optimally, but I have to behave non-optimally in order to know what the optimal thing is. That's the dilemma. So OnPolicy, epsilon soft methods are a compromise between this because they find a near optimal policy that still explores. Jeez. I think I have a cat hair in my nose. Apologies for that. All right. So another approach is to use 2 policies. So you're going to have the target policy, being the learned policy over time, and then we have a behavior policy, which is used to generate the episodes and do learning. So learning from data which is off the target policy is off-policy learning. Okay? Someone asked, so this is similar to the problem with the Sudoku genetic algorithm where it can stuck in local maximum. This is not the same problem as that, and I don't want to conflate the two things. Okay? This is not that whatsoever. All right. So, off-policy methods. On-policy methods are simpler than off-policy methods because it's just one policy that's guiding both things, right? Off-policy methods require additional concepts, higher variance, and converge slower than on-policy methods. But off-policy methods are more powerful in general than on-policy methods. On-policy methods can be considered a special case of off-policy methods where the policies just happen to be the same, okay? And we're not going to go too detailed into off-policy explanation, but I will give an off-policy algorithm that you will be actually implementing in assignment 5. All right, so that's on-policy versus off-policy methods. Just give me 1 second here. I'm just going to deal with this. Just give me 1 second. All right, I'm back. So the next topic for this lecture is temporal difference learning. This is chapter 6 in the reinforcement learning textbook, and it's very, very important. Temporal difference learning is pretty awesome. All right, temporal difference learning is a central idea of reinforcement learning. It combines ideas from Monte Carlo and from dynamic programming. So like Monte Carlo methods, temporal difference methods can learn directly from experience without a model of the environment. But like dynamic programming, temporal difference methods their update step incorporates other learned estimates without waiting for the final outcome of an episode. We also call this bootstrapping. So this relationship between temporal difference learning, Monte Carlo methods, and dynamic programming is important. So essentially, temporal difference learning takes the good part of dynamic programming, which is incorporating value estimates of your neighboring states, with the good part of Monte Carlo, which is learning through experience without needing a model. Okay, so it takes the good parts from both. So, temporal difference prediction. Both temporal difference learning, and I'll just call it TD from now on, so both TD and MC use experience to predict the value of a policy pi. MC methods wait for an episode to finish and then update values based on that final return, right? So this is important. Monte Carlo waits for an episode to finish, right? We wait for the whole episode of Blackjack before we update our values. TD methods do not wait, okay? They instead update values after every single action. So TD will take an action, it'll get a reward, and then it will update values. It won't wait for episodes to finish. So the prediction target, meaning the value we want to learn, for Monte Carlo is the episode return, right? So that means that our previous value at a state was equal to, or our new value at a state is going to be equal to the old value plus alpha, which is our learning rate, times the episode return minus the previous value. So remember, whatever is right here, right? Whatever is right here, that was called our target. Target. All right, that is terrible. Give me a second. I have a better idea. Whatever, my terrible handwriting with a mouse. Whatever this is, that is the target. Okay, that's much better. Temporal difference learning uses the next reward and the next state's value as the target. Okay, so in temporal difference learning, this is the target, right? So this is the big difference. So instead of just waiting for the end of an episode getting the return from that episode and using that as the new target, as the learning target, what we do is we don't wait for the end of the episode, and we take the reward that we just got and we add that to the value of the state that we went to, right? And of course, we have our discounting factor in here, gamma. So TD updates immediately on transitioning to the next state and receiving the next reward. TD's target for the update is this term right here, which is the next reward and gamma times the next state value. And this is called TD0 or one-step TD. If you go through the book, you'll find, I believe it's TD lambda, which is like multi-step temporal difference learning. We won't be doing that in this course. We're pretty much going to stop at the end of this lecture with reinforcement learning. But just know that this is called TD0, and there, you can extend this to care more about things in the future if you want to. So this is the algorithm, tabular TD0, for estimating the value of VPi. Okay, so we showed Monte Carlo for estimating VPi before. Now we're doing temporal difference learning for that. So we have the initialization. So we're going to be given some policy, right? Because this is just for estimating VPi. We're going to be given some policy, and we're going to have an array or some table of values, which is the initial value for each state. Maybe it's 0, maybe whatever. Then the actual update looks like this. We're going to initialize the starting state for an episode, or we can also do this for continuing tasks. Okay, we don't necessarily need it for episodes. Then repeat for each state of the episode, or for each step of the episode. A is the action that the policy says to take. So we look up our policy and we get the action. S prime, that's the next state. So we're going to do the action A at S. R is going to be the reward that we got from doing action A at S. And then our new estimate for this state's value is going to be the old estimate plus alpha times the reward that we got plus gamma times the value of the next state minus the previous state. So this is our learning target right here. Okay? And then we set S equal to S prime. And that's it. We take an action, we get a reward, we get a next state, and then we just use this formula to update our value estimate for that state. It's actually simpler than Monte Carlo. The reason it's simpler than Monte Carlo is because you're doing the update after every action, and you no longer have to store that big episode, right? So TD uses the next state value in its estimate. So V prime of S, remember, VPi of S, this is what we want to know. We want to know the value of doing an action, we want to know the value of a given state given a given policy. And so in Monte Carlo methods, what we said is that is the expected value of the return given a policy. But we saw before, way back, we can turn G of t into, this is just the sum of future rewards, right? So G of t plus 1 times gamma plus the next reward is also that same value. Remember, this here, G of t, is equal to this here. And so G of t plus 1 is just equal to the value at state t plus 1 given a given policy. So Monte Carlo methods use this value, right? That's the target for Monte Carlo methods. Dynamic programming and temporal difference methods use this value as the target. But they end up converging to the same value because they're equal, right? As time goes on, as t goes to infinity, this right here is the same as this right here. And we just derived it. We've derived that throughout the course. It's just that the Monte Carlo method needs to wait for this episode to finish so we can compute the return, whereas temporal difference learning doesn't need to wait. So TD combines Monte Carlo sampling with the dynamic programming update. All right, and that's the power of TD learning. Now, I'm about to, there's a good example in the book, and the example is quite wordy. So what I'm going to do is I'm just going to read out the example from the book. Okay, so I apologize, I don't normally like to just read text from a slide, but this is going to hopefully help illustrate the difference between Monte Carlo updates and temporal difference updates. And the reason I move my camera is because here's the wall of text. So let me take a little sip and then we'll read this out together. Okay. Example, driving home. Each day, as you drive home from work, you try to predict how long it will take to get home. When you leave your office, you note the time, the day of the week, the weather, and anything else that might be relevant. So just say, for example, on this Friday, you're leaving at 6 o'clock and you estimate that it will take 30 minutes to get home. As you reach your car, it's 6:05 and you notice that it started to rain. Traffic is often slower in the rain. And so that you re-estimate that it will take you 35 minutes from then for a total of 40 minutes. 15 minutes later, you completed the highway portion of your journey in good time. As you exit onto a secondary road, you cut your estimate of total travel time to 35 minutes. Unfortunately, at this point, you get stuck behind a slow truck and the road is too narrow to pass. You end up having to follow the truck until you turn onto a side street where you live at 6:40. 3 minutes later, you're home. The sequence of states, actions, times, and predictions is as follows. I do have a cat. There's a cat here in the ear and it's getting stuck to my nose. Apologies. So, here's the state. Here's the elapsed time. Here's the predicted time to go. And here's your predicted total time, okay? So you were leaving the office on Friday at 6. No time has passed yet. Your predicted time to go from this point until the end is 30 minutes. So your predicted total time is 30 minutes, right? If no time has elapsed and you think I have 30 minutes left, then there's 30 minutes to go, or 30 minutes total. I reach my car and it's raining. So 5 minutes later, I reach my car. Now I'm going to estimate that there's 35 minutes left in the trip. So for a total of 30 or 40 minutes. Sorry, so 5 plus 35. Now, later on, I'm exiting the highway. 20 minutes have passed. I now think that I have 15 minutes left to go for a total of 35 minutes. Now I'm on a secondary road and I'm behind a slow truck. So 30 minutes have passed. I think I have 10 minutes left to go. So now my total estimate is 40 minutes. Now, later on, I'm entering my home street. I predict that I have 3 minutes left to go. So that's a total predicted time of 43 minutes. Then I arrive home and it's 43 minutes, okay? So the point here being that as you observe new things throughout this episode of driving home, your predicted time can change, right? So here is what's happening. On the left, here is what Monte Carlo would do. And on the right, here is what temporal difference learning would do. Okay? So for Monte Carlo, what would happen is you just drive all the way home, okay? And you get the total outcome, right? Which is 43 minutes. Then all of your estimates for all of the different states, you would pull them toward that value of 43 minutes, right? None of the context of what happened when when it was raining or you got behind a truck or whatever, Monte Carlo doesn't really care about that. Monte Carlo takes the final episode return and updates all its state values to be closer to that final value. Whereas temporal difference learning does take that context for what happened at each state into account. Right? So as you were leaving the office, you thought initially you were going to be home in 30 minutes, but then when you reached the car, you found it was raining. So your estimate of your state value from leaving the office goes toward that estimate of 40 rather than the final outcome of 43. Okay? Similarly, when you got there and you're now exiting the highway, your estimate went down to 35 because of what happened when you were exiting the highway, right? We are updating our, in TD learning, we're updating our value estimates when we take each action, not at the end of an episode, okay? Now, if we do enough episodes, these will converge to the same value over time, and we average them all out. However, this is the difference in how they actually do their updates. Okay, so the advantages over here are the advantages of temporal difference learning. Let me move myself back up here. So dynamic programming requires a model. Monte Carlo and temporal difference learning do not. Monte Carlo waits until an episode is finished to do the update, but TD is online and incremental, meaning that it doesn't have to wait for it, right? So sometimes episodes can be very, very long, and continuing tasks don't have episodes. So if you don't have episodes, you can't use Monte Carlo because the episode will never finish. TD you can use for continuing tasks because you're updating values after each action. And assignment 5 will actually be a continuing task. So TD methods tend to converge faster than fixed size alpha Monte Carlo methods in practice, but it's not mathematically proven. Okay? So here's a prediction example. Let's say we have 8 episodes. Oh, actually, I'm going to skip this example because I wrote it kind of incorrectly. So I'm going to delete that one. All right. Okay. So temporal difference control now. We just looked at temporal difference prediction, which is the value estimates. How do we do temporal difference control, which is the policy updates? So we've discussed TD for prediction. That means given a policy pi, what is V pi of S? But how do we update the policy? Well, it turns out it's the same thing as for Monte Carlo. We just follow GPI. So like Monte Carlo, we have the same exploitation versus exploration trade-off. And like Monte Carlo, we have on-policy TD control and off-policy TD control. Okay? So on-policy TD control is just like on-policy Monte Carlo. We're going to need to estimate Q pi, so our state action value estimates for the current behavior policy pi, and for all state action pairs, right? Because in order to say which action we should take, I can't just use the values of the states. I need the values of the state action pairs. I need to know how good was doing that action so I can choose which action to do. And we can use the same TD methods discussed previously for updating V pi if I need to. Then we can just update the policy pi to be greedy with respect to Q pi. And that's what we did before, right? So I just take my current estimates for Q pi and I just update my policy to be greedy with respect to that. All right. So SARSA is the first is the OnPolicy TD control algorithm that's first presented in the book. And what SARSA means is the following. Episodes consist of state, action, reward. So we have state, action, reward, state, action, reward, state, action, reward. Okay? Previously, we learned that for TD to transition between episodes, states, and update V, we have V of ST equals V of ST plus alpha times the target minus the previous value. Okay? SARSA, we now need to use, instead of using the values of states, we need the values of state action pairs. So what we do here is the following. SARSA transitions between state action pairs. So this is the update rule for SARSA. We want to update our estimated value for an action at a given state, which is Q of SA, right? So Q of ST AT. So let's say we want to learn up here or estimate the value of doing an action at a given state. Well, that's equal to the previous estimate plus the update rule. But what do we do for SARSA? Well, it's alpha times the next reward that we get plus the value of the next action that we would do. Okay? Minus the previous value. So the target for SARSA is this. Right? So, okay. We're up here in our timeline. We're at a state. We take an action. We get a reward. Then, at the next state, we choose another action. And the value of the action that we chose at that state is going to factor into our target update. Okay? So this is the SARSA update rule. And if we look, what values does SARSA take in order to update its value? Well, it's a state at ST, an action, a reward, then the next state, and the next action. So SARSA, SARSA. So that's how you can memorize the SARSA algorithm if you just memorize the word SARSA, okay? Because it's the previous value plus alpha times the next reward and the value of the next state action pair. Easy. So if ST plus 1 is terminal, then the reward or the value of that is 0. That's the only other update. The policy update is going to be greedy with respect to QSA. And so since we have ST, AT, RT plus 1, ST plus 1, and AT plus 1, SARSA is SARSA. Okay? So SARSA using epsilon greedy, this is almost the same as we had before. So we're going to have initial values for each of our state action pairs, and we just have Q terminal equal to 0. So if we're at a terminal state, that value is going to be 0. Then we repeat for each episode, and this is the pseudocode for implementing SARSA. S is going to be the initial starting state for the episode. We have to start somewhere. A is choosing an action at state S, which is epsilon greedy on all the actions for the given state. Okay, so we use epsilon greedy to select an action at state S. Then, for each state of the episode, this is our first state action. The reward that we get and the next state is essentially take action A at state S. It'll give us a reward and it'll give us a next action or next state. Okay, so that's what these two are. A prime is going to be, now that we have a next state, we're going to choose our next state or our next action from our next state also using epsilon greedy. Okay, so we have a state, we chose an action, epsilon greedy using our policy. Then we got a reward and a next state from that. And we are taking one more action, we're choosing an action, and then we update our value based on that next state and the next action. So QSA is equal to the previous QSA plus alpha times R, which was the reward, plus gamma times the value of doing the next action at the next state minus the previous value. Then we just have to update our current state to be the next state and our current action to be the next action. Okay? So that's SARSA. It's pretty easy. You could implement that pretty easily, I think. Now what we're going to do is we're going to look at QLearning. So QLearning is off-policy TD control. It was invented in 1989, and it was a real early breakthrough in reinforcement learning. It's a really good algorithm. So it's an off-policy temporal difference control algorithm. It's very much like SARSA, however, with one small difference. Here is the update rule for QLearning. The only difference between SARSA and QLearning is right here. So in SARSA, okay, we used the value of the next chosen action at the next state. So we look at the value, we look at the next state, we choose an action of it, and then the value of that action, the one that we actually chose using epsilon greedy, that's what we use to update our state, our value. However, in QLearning, instead of choosing an action from our policy and using that value, we actually look at the next state and we choose the best action from the next state to update our value. So we look ahead to the next state and we say, what's the best thing that I could do at that next state? And whatever the value of that is, that's what I'm going to use to update my value. Okay? So the learned Q value directly approximates Q star, the optimal value function, no matter which behavior policy is being followed. And what this means is that no longer are we taking like those randomized actions from epsilon greedy into account like we did with SARSA. We're choosing the best possible action we could have done at the next state, not like whatever happened to be the next action. So QLearning using epsilon greedy is even easier, in my opinion, than SARSA. So here it is. We have the exact same initialization as SARSA. And here, all we have to do is for each episode, and remember, this does not necessarily have to be episodic. It's just I'm showing you how you would do it for episodic tasks. For each state of the episode, we choose an action at state S using our epsilon greedy, right? Then we get a reward and a next state from taking action A at state S. Then we just implement the QLearning update rule. So our new value estimate for SA is equal to the previous value estimate plus alpha times the reward that we got plus the value of the best action at the next state. Okay? And that's it. Then you set S equal to S prime, and that's literally it. That's assignment 5, basically. So, why is this considered off policy? Okay? So the reason QLearning is off policy, it may not be obvious at first, is that it estimates the value function of the policy generating, if the algorithm estimates the value function of the policy which is generating the data, the method is called OnPolicy. SARSA learns the value of its policy, which does some exploration. However, QLearning learns the value of a policy which does not explore because it takes the maximum action value. Okay? And here's an example of that. So this example is called the cliff. And the cliff is like a 2D grid world, all right? You're trying to get from the starting state over here to the goal state over here, all right? So let me just quickly go over the possible, the description of the thing. So the actions are up, down, left, and right. You're going to get a -1 reward at each time step. If, however, you step over the cliff, you get a reward of -100, and you go back to the start. And this is designed to show the differences between QLearning and SARSA, okay? So, again, if I am at the start, let's say I'm right here, okay? So let's say that I'm currently right here. If I go up, I get a reward of -1. Okay? So again, I'm trying to get somewhere the fastest way. So I have negative rewards and I'm trying to minimize my negative rewards. If I go left, I get a -1. If I go right, I get a -1. But if I chose to go down from here, I step onto the cliff and I get a -100 reward and I go back to the start. Okay? So it's obviously very bad to go onto the cliff, right? So let me just delete these annotations. So I do not want to step onto the cliff. However, while I'm doing my learning, I have to choose some random actions, right? Because we don't know that the cliff is bad until we've experienced the cliff, right? The only reason that I know that a cliff is bad in real life is because someone told me, hey, falling off of that thing would be really bad. I've personally never fallen off of a cliff, right? I have not experienced it. So I'm doing some off-policy learning by someone else knowing someone that fell off a cliff who said that was a big negative reward, right? On-policy learning with a cliff is not cool. So what you would do is, let's say you're currently, you've gone up, you've gone right a little bit, so now you're here. And you're a human, you can see that you probably want to move to the right. But with epsilon greedy, there's a probability that you're going to step onto the cliff, right? So at some point, you are going to step onto the cliff. You're going to see, oh my God, that's terrible. Don't go down. So you give down a huge negative value, right? Even though now we know that going down has a huge negative value, if you ever got back here, for some reason, you'd say, oh, that's a huge negative value, but you still could choose a random action in your exploration and go off the cliff again, right? So here's the whole point. SARSA, when it does its online learning, it is updating values of states with that exploration taking into account, right? So if going down is -100 and going right is -1, so let's say you had a 10% chance of taking a random action, right? So a 10% chance of taking a random action means you have, if you were here, you would have a 2% chance of going downward onto the cliff. So if you have a 2.5% chance of going down onto the cliff times 100, what's that? I guess -2.5, right? It's a negative reward. It's a big negative reward. Or is it -25? Anyway, let's say you had your policy gave you like a random chance to go in any direction. So what SARSA would say is that, oh, I have a random chance of going in any direction, then being on this state is bad. The value of being here is bad because I could randomly choose to go down, right? SARSA's OnPolicy control updates its values to take the randomness into account. Versus, if you were doing QLearning and you were right here, right? If you get this as your next state, so this is going to be your S prime, you don't say, what could possibly happen at that next state using exploration. You would say, what is the best thing that I could do at that state, right? And the best thing you could do would certainly not to be to walk over the cliff. So when SARSA looks at its neighboring state, it says, what could I do with exploration taking into account? So the cliff is a possibility. So SARSA would have worse values for things that are close to the cliff. QLearning, again, I'm repeating myself because it's important, would say, what's the best thing that I could do at the next state? And because the best thing you could do at the next state would be to not walk over the cliff, QLearning would have higher values associated with being close to the cliff. Okay? So what you get in the end is sort of what this diagram shows, is that because SARSA is paranoid, I don't want to say it's paranoid, it doesn't have like those sorts of feelings, but because SARSA knows that it could, during online training, walk off the cliff, it will learn this sort of safe path of going up here and then coming down, right? Because up here, it's very unlikely that you would take multiple random steps in a row and walk off the cliff. So it takes, a little bit more time to get there. QLearning, on the other hand, will learn the best things to do at each state, not taking that randomness into account, and so it will walk right along the edge of the cliff. Okay? So the eventual policy that QLearning learns is better than the eventual policy that SARSA learns. Because if we do all of our training and in the end we just want one policy to follow, QLearning takes the policy that does the optimal thing at every state. But SARSA does the thing that's slightly paranoid because it could take random actions, right? So if we take the policy generated by SARSA, it's going to be worse overall than the policy generated by QLearning. But look at this graph. The online performance during training of SARSA is better than QLearning. Why is that? We just said QLearning is going to produce a better final policy, but during training, you're still using epsilon soft policies. And because SARSA is taking the safe path during training, because it knows about those epsilons, it is actually doing better during training, right? Because training incorporates those random actions. Whereas QLearning is saying, no, go straight for the cliff. I know that the cliff is fine if we do the optimal things, but during training, QLearning is still using epsilon greedy. So while it's training, QLearning can have a lower sum of rewards than SARSA. But if we then take the final policy that was generated by both QLearning and SARSA, and we just run it without epsilon greedy, the QLearning policy will have far better rewards than the SARSA policy. Okay, so I hope that that was a little bit not too confusing. Okay. So someone asked, so QLearning will find the optimal path, but will have a possibility of walking off the cliff only during training, right? If you just take the final policy that's generated by QLearning, it is not doing any of this randomness that SARSA is, right? Because it's updating the policy based on the maximum possible value at the next state. So it's always going toward that one. All right. So QLearning learns the values for the optimal policy, which travels at the edge of the cliff. This results in sometimes falling off the cliff during training because of epsilon greedy action selection. SARSA takes epsilon greedy action selection into account and learns the longer but safer path. So OnPolicy, remember, SARSA is OnPolicy. It's going to learn the values of the policy that guides it, which is the epsilon soft policy. QLearning is OffPolicy. It's not learning the values of the epsilon soft policy, it's learning the values of the optimal policy. Okay? So even though QLearning learns the values of the optimal policy, its online performance is worse. And the reason it's worse during online is because it's not learning to avoid the cliff. Right? Okay. So some possible exam questions here could be, now it's not limited to this, what does it mean to be an off-policy or on-policy RL method? Why is SARSA considered on-policy but QLearning is considered off-policy? Why do SARSA and QLearning produce different paths for the cliff? What are the methods that, like, how does TD compare to MC and DP and why? You need to know the SARSA and QLearning algorithms, and you also need to that update example that we gave. So it's not too much for the exam. That is where we are going to stop for reinforcement learning. However, not before we show assignment 5. All right, so let's start assignment 5 now with the time we have left in the lecture. Assignment 5 should be pretty fun, I think. And here it is. Assignment 5 is a reinforcement learning task, and we are going to use QLearning on Grid World. What you see here is a grid world that's similar to assignment 2, okay? We can move up, down, left, and right. We've got an agent here, and the agent is currently way up here in the top left corner. Using my interface, I can move the agent around, okay? Now, at each time step, the agent is going to get some amount of reward. And that reward is defined in the maps.js file. So let me quickly show you the format for these maps. The default map has a bunch of, you can see here, there are clear tiles. You can move on clear tiles. There are wall tiles, okay? Wall tiles, you cannot walk into them. That is an illegal action. And there are terminal tiles. If you go to a terminal tile, what happens is, this is a continuing task. The agent is always moving around, okay? So terminal tiles they're called terminal, but they don't stop an episode. Instead, if you go to a terminal tile, you actually get teleported to a random place on the map, okay? Our goal is to get to these terminal tiles from anywhere on the map as quickly as possible. And then when we get there, it will teleport us somewhere else and we'll come back, okay? So very quickly, let me show you what this looks like with the solution as it learns. So let me just turn this on. This is the agent moving around. It has some initial policy which says take an action with a random probability. So at first, we're literally taking random actions, okay? When I turn on this, well, let me first refresh this. I'll move the agent over here and I'll say single iteration. So what a single iteration does is it's going to take an action, it's going to record the reward that it got, and it's going to use QLearning to update its values. Okay, so let me quickly, let's look at the tiny environment so we can move the agent over here. Now, up here, there's a mouse mode. Mouse mode has different things we can do. So we could insert walls, we can clear tiles, we can insert a goal, which is actually a terminal node, we can set a reward, or we can move the agent. Okay, so here, for example, let's move the agent over here. If we left click on this tile while print values is the mouse mode, down here you see all the different stats for this state. Okay, so the reward you get for reaching this state is -1. The current values, so the QSA for this state is 0, 0, 0, 0, because our QSA is set to all zeros initially. And our policy for this state is equiprobable random. Okay, so that just means that with a random probability, I'm going to go up, down, left, or right. And what I've drawn on the user interface is for each of the maximum probabilities in our policy, I draw that on the user interface. So because currently our policy says with equal probability, go up, down, left, or right, that's what's drawn right here. Go up, down, left, or right with equal probability. Okay? Now, let me just turn this way up and do some learning real quick. Okay, now I'm going to stop. Once we have learned the optimal policy, it will look like this, where every state in the map should be pointing toward the nearest terminal state. Okay, I'll tell you what all these colors mean in a little bit. Let's go back to the default environment. I'll crank this up to, and what this means is how many iterations of QLearning is happening before I redraw it to the screen. So we're going to turn that way up. We're going to crank it. We're going to let it learn for a bit, and I'm going to stop. And what you can see here is that indeed, the policy is showing where I should go to get to the nearest terminal state. Okay? So, for example, here it says move down. So if I move the agent right there, and then I change my epsilon to 0, so I'm no longer doing any random things, if I do single iteration, it's going to follow to the terminal state, and then when it gets to the terminal state, it's going to teleport me somewhere random on the next iteration. Here, it's going to follow the policy, which will take me to the nearest terminal state. See? So this is what's happening, and if I move this back to 1 and turn it on, you'll see that the agent has learned how to get to the nearest terminal state. Okay, that's the goal of this project. Now, I'll turn off toggle iteration, and let me look at some of the values here. So I can left click when I have print values selected to see the values and the rewards and everything down here. Okay, or I've also built it in so that if you have a middle mouse button, if you middle mouse click somewhere, it will print all of those values for you. Okay, so here is what this looks like if I'm at this state. So this state, what does that look like? Okay, in this assignment, you can move up, down, left, and right at any given time. So even though I'm right here and the tile above me is blocked, up is still a legal action. However, all that will happen is you'll stay still and you'll get a -1 reward. Okay? So that going up is still bad. It's still a choosable action. Down here, you can see the values of doing all of those actions. Okay, so the actions, if I look in my environment, are these right here. So the actions are up, down, left, and right. Okay, up, down, left, and right in that order. Let me see if I can zoom in a little bit here. There we go. So up, down, left, and right are my actions. Okay, I'll go into the code once I've explained things here. So the value of going left is 0. Why is that? Well, it's because the reward that I get from doing an action is essentially this reward value that I have on a state. So if I go back here to my values of my maps, in my default map, everywhere that is not a terminal state has a reward of -1, but if it is a terminal state, it has a reward of 0. Okay? So what does that mean? It means that if I'm here, if I go up, I get a reward of -1. If I go right, I get a reward of -1. If I go down, I get a reward of -1. And if I go left, I get a reward of 0. So that's what these values are here. But those are the rewards, not the values of states, right? So what we end up learning, for example, is if I look here, well, going left has a value of 0 because the eventual return that I will get is 0 because I go straight to a terminal state by doing this, so it's 0. If I go up, I have a -1 value. So going up has a -1 value. Why is that? It's because I get a -1 reward from doing it, so that's the -1, and then QLearning knows the best thing I could do at this state is go left. So I'll get the -1 reward, and then I'll get a 0 reward, and then I'll get to a terminal state. Okay? Now it says going down has a -2 value. Why is that? Well, because going down will give me -1, and then I'm actually have to go another block before I get back to here. So you can think of the values essentially as saying, how far left do I have to go to get to a terminal state? So if I look over here, if I click this one for 8.6, it'll say, okay, the value of going left is -3. That's because I'm 3, if I go left, I'm 3 away from the terminal state. So I go left, 1, 2, 3. Okay? Now, that's kind of intuitive that it would learn these values. Essentially, if I get a -1 reward for each time step, and then a 0 at the terminal state, then the expected value of being at a state is the value, or it's -1 for each time step that it takes me to get to one of these goals. You see that? So the reward is negatively correlated to distance. So if we maximize reward, then we get to these goals faster. Cool. All right. So what these colors now represent is just a shading based on the value of taking actions at states. Okay? So for example, in this color scheme, a 0 value is white. And then the worst possible value on the board, which would be the furthest away from any terminal state, is deep red. And then any value between 0 and the worst value is a different shading of red, right? So here, for example, it would think that going up is the best value because it's white. Going down or going right are equally bad. And going left is a little bit better than going right or going down. And if I click this, you can see that, yeah, so going up has a value of 0, so it's white. Down is a value of -2, so it's a little bit darker. Left is -1, it's like a little bit lighter. And right is also -2, so it's the same shade as going down. So this is purely to help you visualize the values of doing states or doing actions at particular states. That's what that means, okay? Now, what else? Here in the user interface, I forgot to delete this. So we're not going to use this goal reward. I've also built in the ability to give rewards to states, okay? So you can, even though these start out as 0 right here, right? I could give my own, and these start out as -1, I could give my own rewards to individual states. So let's say I want to, for some reason, maybe this is like lava, right? So I can say set reward, and I'll give a -100 reward to that state right here, right? And let me give a -100 reward to that state right there. So these two states now have very negative rewards. So if I turn on the learning for this, it is learning to avoid those states. Okay? So what does this red now mean? Well, remember, red is the worst possible value on the board. So it says if I'm right here, if I go left, I have a huge negative value. Do not go left, because going left gives me minus 100 here, right? Similarly, if I'm right here, don't go left, because going left gives me a huge negative value. So if I happen to put my agent here, and then I turn my epsilon off, and I go single iteration, oops. What's happening now? Okay, so now it's going downward, right? It's avoiding those two states to get to the goal because they have huge negative values, right? So before, everything was -1. Now these things have huge negative values, so I'm avoiding them. Okay, here's another thing you could do, is that right now the terminal states just have values of 0. But maybe I want to give them big positive rewards, right? So for example, if I turn on 100 iterations, and let's see when I start to like peter out down here. So around 25,000 steps is where this starts to get really flat, okay? If instead I give a huge positive reward to getting to this terminal state, so set reward, this state, let's give it like 100 as a reward, and I give this one 100 as a reward, then I do the same thing. Let's see now. Oh, wow. Like within like 7,000 iterations. So in 1/4 of the time, it learned to go here. Now, you might say, oh my God, why is everything green? Okay, just like in the before I had everything red. So red is negative rewards, white is close to 0, and green is positive rewards. Okay, so where it's very green, it's very positive. Where it's very red, it's very negative. Okay, so this will say, we've shown that if we want to reach a goal faster, we give it a big positive reward, and then we learn that going there is better faster. Okay? So yes, we can do it if we just give them all rewards of 0, but it just shows you that if we do set those to really high positive rewards instead of 0s, we will get there faster. Okay? Basically, what this will do is if we have a higher reward for any state on the map than our current highest value, I will want to go to that state. So even if I give a non-terminal state a big reward, right, it will eventually go to that state. So these, I call them terminal, but they're essentially just teleporter nodes. Okay? They're teleporter nodes that go to random places, and wherever I have a higher reward is where I will end up going on the map, and this shows us the policy to get there. So for example, if I do this on the large environment, all of these having rewards of 0, then what I'll get is sort of this flow field, if I crank it up a little bit, of where to go on the map. Okay, so here you saw that, I'm not even going to bother doing that. Someone said both 0 and plus 100 rewards are both greater than -1. So why does the algorithm find plus 100 faster? Well, I didn't necessarily say that it did, but throughout, so why would it, for example, if I set the reward of this to 1 versus 0, right? The reason it finds it faster is because QLearning has this alpha value, right, saying what is the value of this state. So when I get a reward, I look at the next state and I update to go 10% toward that value. So if this is just 0, then if my current value is 0 and I'm trying to update it towards a 0, it's not actually saying go towards here. It's just saying that's not bad, right? So, but if I have a big positive value there, like 1,000 or something, then it'll be like, oh, pull my value 10% of the way toward 1,000. So now my estimate of the value of that is 100, right? Versus the 0 that it used to be. So if these are zeros, essentially it's not saying that it's a good thing to go here. It's just saying it's not as bad as -1. So you tend to gravitate there. But if I give it a positive reward, you're saying it is good to go there, right? So it will learn to go there a little bit faster. I know this is a little bit confusing. But anyway, this is all just using the QLearning algorithm. And it turns out that this is going to be, I think, a pretty easy assignment. All right, so let's go to the code now that we've looked at the assignment. Here is where the maps are defined. And the maps are defined as follows. Tiles in the map are either C for clear, W for wall, or T for teleporting or terminal. Okay, terminal's a bad word. I shouldn't have used that, but whatever, it's done now. So this is how I've defined all the maps. And so, for example, in the tiny map, if I put this as -10, and then I go back and I refresh it, and I load the tiny environment, the value down here, you can see that the reward for 0, 0 is -10 versus the other ones, which are still -1. Okay, so that's how you update the values of the map, or after the fact, you could use set reward to actually type in a reward if you want to. And it sucks, you can't hit cancel, you actually have to type in something. All right, so that's what the maps.js is. Okay. So the next thing I want to show you is the environment class. So the environment class essentially holds all the data about the grid. Okay? So the environment class holds the grid, which is the array of values. It has a height and a width. It stores the actions that are legal. And remember, the actions that are legal are up, down, left, and right. You can always move up, down, left, and right. Okay? It's just that if I chose to move, let's do a single iteration here. So I chose to move up, I bumped into the ceiling and got a -1 reward, right? So let's look at this again. If I'm here and I choose an action, I chose up. Okay? So when I chose up, I got a -1 reward from going up. So now let's look at my values. Well, down here, I got a -1 reward from going up. So, oh, is that still -10? 1 second, maps. No. Why is that printing out that? 1 second, I gotta make sure why. Tiny environment. -1, okay, that worked. So I wanna do this again until I get the same example. Okay, so here I am, I chose to go up. Going up puts me at this state. When I arrive at that state, I get a -1 reward because -1 is down here. Down here now, you've seen that the values of this state are as follows. -0.1000. Why is it -0.1? Why is it not -1? Well, it's because of my alpha, right? So I thought it was -1. That's the target value. But my update function for QLearning multiplies my reward that I got minus my previous value by -1. Or sorry, by 0.1, not -1. So that's why I think the value of going up is -1. Now, if I reload this and change my alpha to 0.5 and I do a single iteration, well, I went down here. So now I got a -1 reward, right? So I think that going down, the value of going down is -0.5 because it's alpha times that value. Now it also incorporates the next state value, but that was 0. Okay? So that's how it works. And over time, it essentially learns what not to do, right? And eventually things start pointing toward the center. That's the whole point of this. Okay. So In the environment, that's the actions that we can do, and this goal reward thing is no longer necessary, so ignore that. There are some functions on the environment that we can use. So getType, if you call like environment.getType with an XY, what you will get is a C, a W, or a T. Okay, that's what you'll get. So that will give you the type of tile that it is. If you want to say get next state, this will perform the next state. So this is done for you. Okay, so you pass in an X and a Y, so that's a given state. So for example, this would be state 2, 0, because it's 2 in the X direction, 0 in the Y direction. And then it will say next X and next Y. It will compute that. And it will say if the next X or the next Y are out of bounds or it's blocked, then take the current state. So for example, if I had said go up here, up would be out of bounds, so it would return the current state. So if the current action makes it go out of bounds or into a wall, we stay at the same state. And that's what that does. This is already done for you here. So this is how you get the next state. And the action that you pass in is going to be the index of the action in this array. So we're usually dealing with indices of actions here. Okay? So if you want to find like the XY change from a given action index, well, you take this dot actions, you index it by that action index, and then the X value is 0 and the Y value is 1. Okay. If you want to get the reward of arriving at a particular state, then you say get reward XY. So let's say that we were right here in our, let me get rid of these colors. It's a bit disorienting. So if we were right here and we chose to go down, the reward that we would get is determined by the reward value of this state right here. So we would say environment.getReward on the next state, and that will give me the reward that I got from doing that action. Okie doke. That's how you get that. Get XY, you'll basically never be calling that because that is used by my other things. Set reward. Set reward is called by the user interface to set rewards. You are never going to call that function. Set type is also called by my things where I can say clear the tile or insert a wall. That's what set type is doing. So you'll never call that function. Get actions, that returns the list of legal actions. So you may want that. That'll return this array up here. Is out of bounds is as before. It will tell you if a specific XY locations is out of bounds. Is blocked will tell you whether or not this is a wall tile. So is blocked will return true for wall tiles and false for other tiles. And is terminal will return true. Yeah, so essentially it checks it. Is blocked returns true for W or wall tiles, and is terminal returns true for T or terminal tiles. Okay, so that's the environment class. That's how you use that. Next, you essentially just have to do this RL student class. And I know it seems a little bit intimidating, but trust me, it's really not going to be that bad. I think that this is actually going to be the easiest assignment, not assignment 4. So all of your assignment code should be in this file. It is the only file submitted. You may create additional functions, blah, blah, blah. Important. Computed actions are represented by an integer. This integer is the index into the this.env.getActions array. Wherever we pass around an action in this class, use the integer index into that array. So what that means is that if I ever want to say the action up, I'll be passing around the index of 0. If I want to say the action left, I'll be passing around the index of 2. Okay, it's just much easier to pass around that single integer than an actual action. Okay. Note, terminal states do not actually terminate an episode. They simply teleport an agent to a random, non-blocking tile on the map. This is because we are working with a continuing task, so technically none of the states are terminal. And a big tip is to complete the assignment in the order of steps listed in learning iteration. Okay, so let's look at some of the variables that we have. We have this.config. This.config is going to hold all of these values that you see here. I'm going to remove this goal reward is an old thing from last year that we are not using anymore. So this will not be present when you get your assignment. That won't be there because I put in this ability to set rewards individually. Okay. So you have this.config.alpha, that's the learning factor, this.config.gamma, that's the discount factor, and this.config.epsilon, that is your epsilon greedy chance to select a random action. This.env, that's the environment. So you'll say this.env.getType or this.env.getReward. That's how you'll get access to that. This.q, so that is your values array, okay? And if I can, oops, geez. So this dot values q, x, y, a, that is the value of doing action A at state x, y. P, that is your policy. So the policy is the probability of doing action A at state x, y. And out here, if I middle mouse click on something, it will show me the reward value for that state. It will go through Q, and that is the values printout here, and it will go through P, and that is the policy printout here. Okay, so what you see here is this is literally just printing out this.q for values and this.p for policy. All right, and this.state, that is the current location of the agent on the map. So, unlike assignment 2, where you just drew paths between two locations, in this assignment, your agent actually lives in a place on the map. It takes an action, and then its place on the map is updated. Okay? And so right here, that is how you know where the agent is. It's this.state, and it starts out at 0, 0. Then what happens is in the constructor, the initialize function is called. And what initialize does is it essentially takes the environment width and height and sets up first, it initializes all the QSA values to 0, and then it initializes all of the policy to be equiprobable random. And the way it does that is for each policy, so you see here for each x, for each y, that is the x and y, so that's each state of the map. Then for each action at that state, it sets the policy to be 1 divided by the number of actions.length. So the reason you see 0.25, 0.25, 0.25, that means with 1/4 probability go up, with 1/4 probability go left, with 1/4 probability go down. But after we've done an action here, right, I've got one value that's worse than the rest, and so you will have to update the policy to be equiprobable random for all the maximum possible actions. And we went over that 2 lectures ago. So I'll show you the function that does that. So this is done for you, right? The setting up of Q values and P values is done for you. This is the function that you basically have to do, and I've spelled it out for you. Paint by numbers, okay? So this function performs one iteration of QLearning. So this learning iteration function, if you click single iteration, then it will do a single iteration. It'll call that function once. If you click toggle iteration, it will do that 60 times per second. However, if you turn this up to 100, it'll do 100 iterations 60 times per second. Okay, so that's what that does. The learning iteration function is what matters. And in here is where you do QLearning generalized policy iteration. And just another important note is the computed actions are represented by an integer. This integer is the index into the this.env.getActions array. Wherever we pass an action in the class, use the integer index. Okay, so my cat is screaming to get out. If you can give me 1 second, I'll be right back. All right, the cat is happily outside now, not screaming from the kitchen. Okay, so what you have to do are just the very simple steps of policy iteration. It looks like a lot, but it's really not that much stuff. So the first thing you have to do is if the agent is on a terminal state, you have to set it to a random legal state. And all that means is, so if the agent is currently on a terminal state, when you do an action iteration, okay, or a learning iteration, you just have to find a random non-blocked non-terminal state to send the agent to. See how that works? So that's what you have to do. So you'll say something like, if this .env.is terminal, let's see here. I'll help you out with this. So we'll go over here, is terminal, X and Y. So if this .env.is terminal, and then I would say this .state 0, this .state 1. So now we know that the agent is at a terminal state. So what you would do in here is you would generate a random state, and if it's still a terminal or blocked state, do another one. So while the state I've generated is not terminal and it's not blocked, generate a new random state and just send them there, okay? And then after that, you would return. So you do not want to continue with this learning iteration if you did that random teleportation thing, okay? So you're randomly teleporting to somewhere on the map. Pretty easy to do. That's step one. Step two, select an action A to perform from our current policy. This will be stored as the integer index of the action. And, oh geez, hang on, view, where's the zoom out? Appearance, zoom out, control minus, I did that before. Okay, here we go. This is a bit better. So you select the action from the policy inside this .select action from policy, okay? So there's a function down here, which is select action from policy. And this is what you have to do. This function should select an action from, this function should select an action to perform at a given state, given the current policy and epsilon greedy this.config.epsilon value, okay? So down here, you're going to initially have some max value action index. You're going to choose the action based on epsilon greedy and the probability stored in the policy. So PXYA is the probability of choosing action A at state XY. So we choose randomly from all the actions which have the maximum probability and return its index. So what this means is that right here, you would say let random equals like random between 0 and 1, however you do that. If random is less than this.config.epsilon, return random action, right, between 0 and this.actions.length. Otherwise, you have to go through the policy. So you say for let A equals 0, A less than this.env.getActions.length, A++, so that's how you iterate through actions. You would get let policy, the probability of choosing this action is equal to P, this.p x, or the state, state 0, state 1, and then A. Okay, so that's how you get the probability. So this is the policy. This is the X and the Y location of where you currently are, what state you're at. And this is the loop of how you loop over actions. So you go back in the slides and you figure out how we did this. Okay, so for example, if you have, if your P was equal to something like 0.500, 0.5, you figure out which indices of the policy have the maximum values, And then you would say, I don't know, like you'd call that M or something. So you would say 0 and 3, right? Because 0 right here and 3 have the highest values. And then you select return random value from M. So this means that since index 0 and index 3 of the actions array have the maximum values, if you return a random one of these, that is the action that our policy tells you to do. Okay, so that's how you would do that function. Okay, so that is step 2. That's selecting the action that you should do from your policy. Next is to calculate the next state by doing action A at state S. And this is just this.getNextState, right? So getNextState is here. The action is here. That's the action that you should do, okay? Let me remove this, because in environment, I've already given you a getNextState thing. So I guess that's already done for you. So I guess you don't need that anymore. Let's remove that. And this is this.env.getNextState. All right, I did part of the assignment for you. Great. So you just call this.env.getNextState with the action that you return from the policy. Next, you get the reward from doing action A at this state from the environment. So the reward you get is the reward value of the next state. And it's just this.env.getReward. Okay, so that's it. I'm not going to type it out for you because that's one line of code. Step 5 is you update your current Q value based on the QLearning update rule. And that's this.update value. So if we go down to update value, we have a state, we have an action that we did at that state, we have a reward that we got from doing that action, and we have a next state. Okay, so we look in our slides, and here is the update rule. So you take that, and you put it over here, and you turn it into JavaScript, right? So instead of QSTAT, that would be this dot Q state 0, or you could even do this. Let X equal state 0, let Y equal state 1, and then this dot Q X Y equals this dot Q X Y plus this dot config dot alpha times, and then you do the rest. Okay? The only thing you have to do in here that's not a literal one-liner is you have to look through your Q value estimates for each action at next state. So for each of your 4 actions at the next state, you look up the Q value for each of those actions and you record the maximum of those. And that's what goes in here. Okay? This max A, that's where you record the value of the maximum valued action at that state. That's like the only difficult part of this right here. Okay, let me undo all that. So I basically just did that for you. And the next thing you have to do, so you've updated the Q value. Now you update the current policy at that state. And that is this.update policy. So now you have to update the policy at the state. So you have X and Y from the state. Now what I'm saying is, here's the pseudocode to do this. Let's say that our policy, or our action value, so our QXY was equal to like 0. Let's say it was 10, 8, 10, 7. Okay, let's just say that those are the values here. Here's what we need to do. Eventually, our policy at XY needs to be equal to, well, we look at all the values that maximized this. So we have a 10 here, and we have a 10 here, and there's 2 of them. So we should have a 0.5% chance of choosing those, and a 0% chance of choosing the others. Okay? So you're going to take this, what you have, and turn it into this. All right? And the pseudocode for doing that is, first, record the max action value. So get the maximum value from all of the actions at that state. Then you're going to make an array of the indices of the actions which maximize that value. And then for each action, if it's one of those maximum actions, you just take 1 and divide it by the max actions.length. Otherwise, it's 0. And that's exactly what we went over in the slides before, and it's exactly what I just showed you here in those 2 lines of code. Now we've updated our policy, and the last thing we have to do is just say this.state equals next state, if that's what you called it. Okay, so that the GUI will actually draw it at this next state. So if I went left, now it's here. If I went up, now it's here. So this is really all you have to do for the assignment is these things. You implement them in these functions. It's very easy to read, and it should be pretty easy to implement. Okay, all you have to do is this update rule from QLearning and be able to index an array. So that's it. That's the assignment. And then you should be able to do this, where you crank this up, hit toggle iteration, and eventually everything should be pointing at the terminal nodes. Or technically, everything should be pointing at the states that have the highest reward value. And it makes intuitive sense to set the rewards here to those values, right? Oh, something else that I wanted to show you, which is pretty cool before we go, is let's say we have this large environment. Let me do some learning on this large environment. It's 10,000 per update, so it's just a little bit slow. Now, because this is a stationary environment, if I actually pump alpha up, I'll show you how much faster the learning is. All right, so I'm going to go to large environment. I'm going to change alpha to 0.5. I'm going to do more exploration. I'm going to do 1,000 iterations here, and it should learn a lot faster. Yeah, it does end up learning a lot faster if you pump up alpha because it's a stationary problem, right? Our rewards are never changing. But just watch this. So all of these down here. So these states down here, there's this, you can see this sort of red line. And at this red line, what that red line represents is anything below that red line is closer to this terminal state. And everything above that red line is closer to this terminal state, right? So it's cool that you get to visualize your action values. But watch this. If I insert a wall down here, and then I keep learning, what will happen is, as it will learn that going up to this one is better. See them changing? So we've changed the environment, and I can actually change the environment like in real time. And you'll see it learning in real time what to do. So let's clear a tile up here. And it will eventually learn that as well. Let's clear a bunch of these tiles. Now, it takes a while to visit these because the policy before said not to visit them, but it does end up learning. So that's pretty neat. It will learn in real time as you make changes what to do or not what to do. And the coolest thing is if you actually insert, well, I say insert goal, but it's actually terminal. If I insert a goal here, it's now thinking that you should go to this goal, right? So those things will eventually change as we do random actions and explore to go there. And if I pump up epsilon, you'll see it learn this a little bit faster, right? So it's slowly learning over time that even if we update this environment in real time, it's showing us that, which is pretty neat, I think anyway. All right. And a little treat for the grad students, because the grad students have a project to work on. There is no bonus requirement for the grad students for this assignment, okay? The grad students don't have to do anything extra. I think this will be sort of a chiller assignment than most. And you have 16 days to work on it, but it's due on the last day of class. So you have more than 2 weeks, but don't leave it till the last minute. You could get this done in a weekend, but don't leave it till the last weekend. Okay? All right, that's it. Thank you so much for tuning in, and I'll see you in the next one.